So imagine stepping out your front door in San Francisco. It's this brisk, foggy, 63-degree morning.
Oh yeah, you definitely need a sweater.
Right. You're holding a hot coffee, shivering a little. But now imagine getting in your car, driving just 1 hour inland toward the Central Valley, and stepping out into a literal 108-degree blast furnace.
It's just
It
wild.
is. Because, you haven't changed latitudes, you haven't crossed some massive mountain range, but you've just traveled across a 40-plus degree temperature gap.
Yeah, that kind of gradient is just incredible to see in such a short distance.
Exactly. And when we look at the August 8th, 2026 weather report from the Daily Tech Reader, that is the kind of meteorological battlefield we are dissecting today in this deep dive.
Battlefield is honestly the right word for it.
We're looking at this atmospheric landscape that is deeply fractured, highly volatile, and just operating at absolute extremes.
Yeah, it really is a masterclass in planetary physics, like
Hmm.
playing out in real time for us.
Mm.
We're seeing this massive atmospheric blocking pattern, locking up the western half of the continent.
Like a giant roadblock.
Right, a complete atmospheric roadblock, and that's triggering this cascade of secondary effects.
Yeah.
I mean, we're talking everything from cross-continental smoke migration to really intense localized moisture loading along the eastern seaboard.
Wow.
So the data today doesn't just show us isolated weather events. It reveals this highly reactive, interconnected global engine. Extreme heat in one zone is literally forcing a dramatic and sometimes violent response thousands of miles away.
Okay, let's unpack this, because if we want to understand the invisible engine driving today's extremes, we kind of have to start at the source of the trauma, right?
Absolutely, the anchor point.
Yeah, and looking at the data, the core of that trauma is just sitting over the desert Southwest and Mountain West. We are looking at staggering numbers today.
Oh, they're brutal.
Las Vegas is hitting 112 degrees. Phoenix is under an extreme heat warning at 111. And Lake Havasu, they're pushing 115.
It's just oppressive. And even places further north, like Denver, they're sitting right at 99 degrees today.
Which is just crazy for that elevation. I kind of visualize a high-pressure system of this magnitude, like a heavy iron lid on a boiling pot that just won't budge.
That's a great way to picture it, yeah.
It physically compresses the air column, right? It traps all that thermal energy down at the surface and totally deflects any of those cooler, larger weather fronts that might actually try to move into the region.
Yeah, that compression is a really crucial mechanism here. Because as that air subsides or sinks under the high pressure, it warms adiabatically.
Adiabatically, meaning like...
Basically, the air is getting physically squeezed. So you aren't just getting solar radiation heating the ground from the sun. The atmosphere itself is physically squeezing the air and heating it up.
Wow, so the sky is acting like a giant vice grip.
Exactly. It creates this massive self-sustaining dome of descending hot, dry air. And because it deflects the jet stream so far up to the north, it completely starves the entire region of any cloud cover or rain that might, offer a reprieve.
Which brings me to the detail in this report that I think is, frankly, the most alarming. It's not just that 112-degree afternoon peak in Vegas.
You're talking about the overnight lows.
Yes. The forecast notes that the overnight temperature in Las Vegas will only drop to 89 degrees.
Yeah, 89 degrees at the absolute coolest part of the night.
Right. And when you have a highly urbanized environment, like miles of concrete, asphalt, steel, glass, and your ambient air temperature at 3:00 a.m. is still hovering near 90 degrees, how does that fundamentally alter the thermal dynamics of a city compared to just, a standard hot day?
Well, what's fascinating here is the total failure of the diurnal temperature cycle to properly reset.
Yeah.
And that's primarily due to the thermal mass of all that urban infrastructure you just mentioned.
So the buildings themselves are the problem?
Essentially, yeah. During the day, under that iron lid you described, the concrete and asphalt absorb an immense amount of shortwave solar radiation. They act like massive thermal batteries.
So they're just soaking it all up.
Right. They store all that kinetic energy deep inside their structures. Now, usually after sunset, the ambient air temperature drops significantly, which creates a steep temperature gradient.
Okay, so if the air gets cold, the buildings stay hot.
Exactly. And that gradient allows the infrastructure to efficiently radiate all that stored energy back out into the cooler night air and eventually out to space.
But if the surrounding air is already 89 degrees at its coldest point, that gradient is basically erased, isn't it? The thermal battery has nowhere to discharge its energy.
That is the exact problem. The transfer of heat slows to an absolute crawl. And the urban geometry actually traps it even further.
Urban geometry, like the layout of the streets?
Yeah, the tall buildings and narrow streets create these quote-unquote urban canyons. They reflect that emitted radiation back and forth between the walls instead of letting it escape upward.
Oh man, so it's just bouncing around at street level.
Yeah, so the buildings and the pavement are still physically radiating heat at dawn, right when the sun comes up and starts pumping energy back into them all over again.
So you start the very next day with that elevated baseline of heat. The city is basically compounding its thermal debt.
Exactly. Compounding is the perfect word.
I have to imagine the cascading effects of that are severe, especially on, like, the power grid. Your air conditioning units are never getting a low load cycle.
No, not at all. They are fighting the ambient air temperature and the radiant heat from the walls simultaneously. They're running at maximum capacity 24/7.
And physically, I mean, the human body relies on that nighttime temperature drop to shed its own core heat. If you're constantly surrounded by 89-degree air, your cardiovascular system never stops working overtime to cool you down.
It creates a super dangerous cumulative stress load on both the infrastructure and the population. And when you zoom out from those urban centers to the broader geographical region, that prolonged heat fundamentally alters the landscape itself.
It dries everything out.
Aggressively. It draws all the moisture out of the soil and the vegetation, which drastically lowers the fuel moisture content.
Which sets the stage for the next major anomaly in this report. Because you look at the Mountain West Cheyenne is at 99 degrees today, Casper is at 101.
And both are under critical fire weather warnings.
Right, because of single-digit relative humidity and gusty winds. The heat dome has effectively turned millions of acres of forest into tinder.
Yeah, a massive powder keg.
And we're seeing the combustion of that tinder in real time with the huge wildfires currently burning across Oregon. The report shows the smoke degrading air quality heavily in the Pacific Northwest.
It's really bad up there right now.
Yeah, Spokane is at 84 degrees, Boise at 92, and both are dealing with severely restricted visibility in the Columbia Basin.
The localized atmospheric impact of that smoke is intense. It can actually suppress daytime high temperatures slightly by physically blocking the solar radiation.
Oh, interesting.
Yeah, which is why Portland might be trending down just a bit to 88 degrees today.
But the report doesn't just show the smoke hovering over the Pacific Northwest. It notes that the smoke haze is migrating thousands of miles eastward, affecting the skies all the way in Fargo, North Dakota, and Sioux Falls, South Dakota.
Which is an incredible distance.
Right, and I'm looking at this and I have to push back a bit on the physics, because we tend to think of weather as our own local problem. But smoke traveling from western fires all the way to Fargo proves we're sharing one giant messy atmosphere.
We really are.
But I'm stuck on the sheer mechanics of this. Gravity exists, right? We are talking about physical particulate matter ash soot, incinerated carbon generated by a fire in Oregon.
Heavy stuff, relatively speaking.
Exactly. How does all of that heavy material avoid simply settling to the ground over Idaho or Montana? How is it staying airborne and concentrated enough to haze out the sun halfway across the continent?
Well, if we connect this to the bigger picture, that is a critical question about atmospheric fluid dynamics. It basically comes down to three things: particle size, updraft velocity, and high-altitude transport.
Okay, walk me through that.
First, the intense thermal energy of a massive wildfire creates these violent, localized convective updrafts. It's essentially a heat engine. The fire heats the air so rapidly that it shoots upward, sometimes creating its own weather system, which we call a pyrocumulonimbus cloud.
A fire cloud. That sounds terrifying.
It kind of is. These updrafts act like a giant atmospheric cannon, injecting millions of tons of microscopic aerosol straight through the boundary layer and high into the upper troposphere,
How high are we talking?
sometimes reaching altitudes of 30,000 to 40,000 feet.
Okay, wow. So it's completely bypassing the lower atmosphere. It's injecting the smoke directly into the fast lane.
Precisely. And at those altitudes, you're interacting with the polar jet stream, or upper-level westerlies. Those are rivers of air moving at incredible speeds from west to east.
But what about gravity? Why don't the ashes just fall?
Right, regarding gravity, the particles that actually make it that high are extraordinarily small, often less than 2.5 microns in diameter. For particles that microscopic, the aerodynamic drag forces from the surrounding air are significantly stronger than the downward pull of gravity.
So they just float on the wind current.
Yeah, their terminal velocity is so incredibly slow that as long as they are caught in those fast-moving upper currents, they can remain suspended for days, traveling vast distances before they finally coagulate and settle out.
That paints such a vivid picture. You have Fargo experiencing a perfectly pleasant 82-degree day at the surface,
Hmm.
but 30,000 feet above their heads, the stratosphere is acting as a high-speed conveyor belt for the ashes of an Oregon forest.
It really shatters the illusion that our local weather is actually local.
Totally. Here's where it gets really interesting, though. If the smoke shows us how massively connected the continent is, California is currently demonstrating the exact opposite phenomenon.
Oh, California is a whole different beast today.
Yeah. The data coming out of there today is just bizarre. The state is exhibiting violently disconnected microclimates existing practically on top of each other.
Yeah, the topographical and thermal gradients out there create one of the most complex, localized meteorological setups on the planet.
Look at these numbers from the report. The Central Valley is an absolute furnace. Fresno is at 106, Bakersfield is 105, and Redding up at the northern end of the valley is hitting an extreme 108 degrees.
Just baking.
Even Sacramento is holding that 103 under a heat advisory. But then you look at coastal San Francisco, which is locked under a marine layer at a very cool 63 degrees.
That contrast is amazing.
That is a 40-plus degree temperature difference over a distance of fewer than 60 miles. Like my example earlier, it's like walking out of a dry sauna directly into a walk-in refrigerator just by driving an hour down the highway.
It's a surreal experience if you've ever driven it.
I bet. And my deduction here is that these two extremes aren't just coincidentally happening near each other, they have to be interacting. How does the 100-degree heat inland not simply radiate outward and, incinerate that 63-degree marine layer on the coast?
Well, your deduction is spot on. The intense heat inland is actually the engine powering the refrigeration on the coast.
Wait, really? The heat creates the cold?
Yeah. It operates on this massive pressure gradient. First, we have the California current, which drives deep, frigid Pacific Ocean water up to the surface along the coast through a process called upwelling.
Okay, so freezing water near the beach.
Right. And the air mass sitting immediately above that freezing water is chilled to its dew point, creating a dense, heavy marine boundary layer. It's essentially a thick slab of cold fog.
So you have a dense, heavy block of cold air anchored over the ocean.
Yes. Meanwhile, in the Central Valley, the intense solar heating creates a thermal low. As the air of the valley superheats, its density decreases and it rises aggressively.
Which leaves an empty space behind.
Exactly. It creates a massive void of pressure at the surface. And the atmosphere abhors a vacuum. So to fill that void, the inland thermal low literally sucks the dense, heavy marine air from the ocean, pulling it violently through any available topographical gap.
Like the Golden Gate Bridge.
Exactly, like the Golden Gate.
That makes perfect sense. The hotter the Central Valley gets, the stronger the vacuum becomes, and the harder it pulls that cold ocean air on shore. But that still leaves the question of the boundary itself. When that 100-degree heat physically meets that 60-degree fog, why doesn't the heat just overpower it and evaporate the fog?
It survives because of a very specific meteorological mechanism. Marine temperature inversion.
An inversion, so things are upside down.
Precisely.
Yeah.
In a standard atmospheric profile, temperature gets colder as you go up in altitude. But here, the high-pressure dome we talked about earlier is causing hot, dry air to subside over the entire region.
The iron lid is back.
The iron lid is back. And this descending hot air acts as a secondary lid, resting directly on top of the dense, cold marine layer. Because the cold air is so much heavier and denser, the hot air just glides right over the top of it, rather than mixing in.
So it creates a physical stratification, like oil and water.
Exactly like oil and water. The boundary between that heavy, cold fog at the surface and the scorching, dry air up above becomes incredibly sharp. It acts as an impenetrable thermodynamic barrier.
Wow.
The hot air above can't penetrate down, and the cold fog below can't rise to mix out. So San Francisco remains trapped under this stubborn 63-degree gray ceiling, completely shielded by the inversion gap.
While just a few dozen miles inland, Redding is baking at 108 degrees under a blazing sun. It's a literal wall of thermodynamics separating the two cities. The scale of those forces is just incredible.
It really is.
And yet, as we move eastward in today's report, the atmosphere completely changes its personality again, doesn't it? We swap the dry, static oven of the west for a volatile, suffocating steam room in the south and east.
Yeah, we're transitioning away from sensible heat, which is the dry heat you can just measure with a standard thermometer, into the realm of latent heat.
Latent heat? What's the difference?
Latent heat is where massive amounts of energy are hidden within atmospheric water vapor. It completely changes the behavior of the heat.
And the numbers in Texas and the southeast reflect that shift immediately. Dallas is at 99 degrees with a 35% chance of a storm. Austin is at 101.
And Houston is sitting at 97 with just oppressive Gulf humidity.
Right. Oklahoma City and Tulsa are in the upper 90s, but they're facing super dangerous heat indexes because the moisture drastically alters the biological impact of the temperature.
It feels so much hotter than the thermometer says.
Exactly. And you follow that Gulf moisture streaming north, and New Orleans and Baton Rouge are sitting at 91 degrees with a 45% storm chance. Mobile and Pensacola are remaining totally unsettled.
Florida's mechanics are firing on all cylinders today, too.
Yeah, Miami, Fort Lauderdale, West Palm Beach are all around 90 degrees. Orlando at 92 and Tampa at 91 are experiencing these quote-unquote sea breeze boundaries, triggering isolated afternoon cells. Thankfully, no immediate tropical threat in the Atlantic, but the moisture is everywhere.
The entire eastern seaboard is caught in this deep southerly flow. It's continuously pumping saturated marine air over the landmass.
Which brings us up the East Coast. New York City is at 90 degrees, and just like Las Vegas, they are dealing with brutal overnight lows, barely dipping below 76 degrees.
Which just keeps the atmosphere totally loaded with moisture.
Boston gets a slight reprieve at 85 degrees thanks to an onshore flow. But the mid-Atlantic, man, Washington, D.C. is climbing to 91 degrees. And the report uses a very specific technical phrase for the D.C. forecast.
Oh, I know the one you're looking at.
It states that intense daytime heating will destabilize the boundary layer, leading to late afternoon convective storms. So what does this all mean?
It sounds super technical, right?
Yeah. If I am standing in Washington, D.C. at 3:00 p.m., looking up at a hazy, muggy sky, what is actually happening from a physics perspective when that boundary layer, quote-unquote, destabilizes?
This raises an important question about convective available potential energy, or KE. When we talk about high humidity in the east, we aren't just talking about discomfort.
No.
No, water vapor is essentially stored solar energy. Think about it. When water evaporates from the Gulf of Mexico, it has to absorb a massive amount of heat to physically change from a liquid to a gas.
Okay, that makes sense.
That heat energy doesn't just vanish. It is now locked inside the water vapor molecules floating over Washington, D.C.
So it's like an invisible reservoir of fuel just waiting for an ignition source.
That's a perfect way to look at it. Now, similar to California, the East Coast often starts the day with an inversion cap.
Another lid.
Right, a layer of slightly warmer, stable air a few thousand feet up that traps this humid, fuel-loaded boundary layer near the surface. Throughout the morning, the sun beats down on the concrete and asphalt of D.C., heating that saturated air at the surface.
And as it heats up, it wants to rise.
It becomes incredibly buoyant. It pushes up, but it keeps hitting that invisible lid, that inversion cap.
It's testing the structural integrity of the atmosphere. The pressure is just building and building.
And destabilizing the boundary layer is the moment of failure. It means the surface air has finally absorbed so much thermal energy that its upward momentum violently punches right through that inversion cap.
Boom!
Boom! The moment it breaks through, that superheated, hyperhumid air rushes upward at incredible speeds, sometimes 50 to 100 miles per hour, straight up into the freezing upper troposphere.
And what happens when it hits that freezing air?
The water vapor rapidly condenses back into liquid water.
Wait, and when it condenses, does it release all that stored latent heat it originally absorbed from the Gulf of Mexico?
Exactly. You nailed it. That massive release of latent heat warms the surrounding air up there, making it even more buoyant, causing it to accelerate upward even faster.
So it feeds itself.
It is a self-feeding thermodynamic explosion. Within 30 minutes, a hazy, stable sky transforms into a 40,000-foot cumulonimbus tower, producing torrential rain, severe lightning, and microbursts.
It's the exact same mechanic as shaking a bottle of warm carbonated soda and finally popping the top. The daytime heating is what pops the top on the atmosphere.
That's a great analogy.
And understanding that latent heat release explains why those sea breeze boundaries in Tampa operate the exact same way. The cooler marine air from the Gulf of Mexico pushes inland, acts like a dense physical wedge, and literally shoves the hot, saturated inland air upward until it forces it through the cap.
Yep, triggering those explosive afternoon thunderstorms along the I-4 corridor. It is the atmosphere violently resolving an energy imbalance. Heat, moisture, and pressure are constantly seeking equilibrium.
And the sheer volume of energy in the system right now means that resolution is happening via extreme volatile convection. It is an incredible amount of kinetic and thermal energy to try and conceptualize.
It really is.
I mean, we've mapped out a country that is baking under an immense atmospheric compression dome in the west. choking on high-altitude smoke transport in the Northwest, fractured by staggering 40-degree thermodynamic walls in California, and acting like a shaken soda bottle of latent heat along the eastern seaboard.
It paints a totally daunting picture, I know. But the data does highlight a few pockets where the atmosphere is offering a brief window of stability.
Oh, for sure. We should definitely give a nod to the Midwest for holding it together today amid all this chaos. After a turbulent week, Chicago is catching a beautiful break, sitting at a highly comfortable 80 degrees with mostly sunny skies.
Yeah, that's gorgeous.
Minneapolis is also holding near 80 degrees, though the forecast notes they have a new front rolling in ahead of a Monday storm pattern. But for today, they get a brief pause in the extremes.
And honestly, analyzing all of this, the high-pressure lids, the aerosol transport, the marine inversions, the latent heat, this is why decoding the mechanics matters so deeply to your daily life.
Because it's not just trivia.
No, weather isn't just a static icon on a phone app. Whether you are trying to understand why your late afternoon flight out of Florida was suddenly grounded by a towering storm cloud, or why your air conditioning unit is failing to keep up at 2:00 a.m. in New York City.
Or why the sun looks like a strange apocalyptic red disk through the haze in Fargo.
Exactly. It is all tethered to the same global engine. Once you understand the physics driving the moisture and the heat, you aren't just reacting to the weather anymore. You are witnessing the fluid dynamics of our planet operating in real time.
It fundamentally changes your relationship with the sky above you. You see the cause and the effect, not just the symptom. And I want to leave you with one final thought and mull over today as you look at your own local forecast.
Okay, what is it?
Well, we discussed how a quote-unquote minor dip in the southwestern heat dome next week still leaves millions of people facing a deeply dangerous 110 degrees. We discussed how 40-degree temperature gaps are being sustained over just a one-hour drive in California.
Right.
If these intense localized extremes and compounding heat debts are not just anomalous flukes, but the new baseline of our atmospheric engine, how are we going to adapt structurally?
That is the million-dollar question.
How will our architecture, our urban planning, our power grids, and just our daily societal routines have to permanently evolve in the coming decades to withstand a world where an 89-degree overnight low isn't a record, but just a normal Tuesday? The weather isn't just a backdrop to our lives anymore. It is the primary architect of our future infrastructure.
It represents the ultimate forcing function for human adaptation and engineering. We will have to design our cities to work with these thermodynamics rather than constantly fighting against them.
A massive engineering challenge for the years ahead. Think about the invisible engine driving those extremes the next time you step outside to check if you need a jacket. Thanks for joining us for this deep dive into the atmosphere, and we'll catch you next time.